Okay, so thanks very much for the invitation. It's a pleasure to be giving this talk here. So when I was asked to give a talk on this conference on metric and analytic aspects of moduli spaces, I was a bit hesitating, as even though more than 10 years ago now I was working with Rafe and Eugenie Untitled and Rafe Mazzeo on analytic aspects of some of these moduli spaces, maybe even the metric aspects. But more recently I have diverged and have been studying the same spaces, but from more arithmetic, representation, theoretic, and maybe topological point of view. So what I then decided to do is to show you some of these 3D printed toy models I have been doing basically for fun. And so in the process of producing some more, partly for this lecture, I acquired the equations defining them from Sergei Cherkis, and then somehow accidentally, or research also had, so we obtained some observations on the geometry of these. So this is a lucky coincidence that now I can give also the fun part of the talk and a little bit more research, new research with Michael Wong and Dimitri Viss in the second part. Okay, so let me first try to explain you why I am interested in toy models. So the idea is that, so first, the general problem I have been studying is to understand the geometry and topology of hyperkähler moduli spaces in general. Let me just first say that there are three major class of examples which all arise from mathematical physics. So the first perhaps which was studied is the moduli space of instantons on R4 or on ALE spaces, then magnetic monopoles on R3, and finally Higgs bundles equations on a Riemann surface in 2 dimensions. So this is the source of the spaces. Then we are interested in really just as examples to explain the geometry and the topology that we have been recovering by research was to understand toy models, examples of these moduli spaces which are understandable by other means. So if I want to study the topology of a moduli problem, then well, you have to really understand the moduli problem. But if you can describe your space by other means, then you have other ways to understand its topology. So the 4-dimensional, the smallest dimensional examples are really useful. And so the 3 class of metric asymptotics we expect to see in these 3 classes of problems are asymptotically locally Euclidean, ALE, ALF, and ALJ, which we have seen already this conference. I'm not even going to go into details, but these are the 3 classes of asymptotics of these 4-dimensional hyperkähler manifolds. So what we are interested in first and mostly is their topology, try to understand their, say, cohomology in general. So originally, when we did this work, we were interested in L2 cohomology, that is space of L2 harmonic forms, which had the origin in physics. But then I changed basically to try to do arithmetic studies, and then it was more natural just to look at plain ordinary topology, cohomology of these spaces. So then, now with technology, what we can also do, if you can work out hard what is the defining equation, for example, of these varieties or other means, one of my little side projects is try to visualize these toy models by 3D printing real slices. So we take complex a hyperkähler manifold. In one of the complex structures, we write down maybe an equation, and you have to play with the equation to get the real part nice, and then you try to print the real part. And the hope is that this is going to capture the topology of the four-dimensional gravitational instanton. Okay, so now just in very schematically, let me go some more details on these hyperkähler moduli spaces. As I already mentioned, these studies basically all started by the study of moduli spaces of Young-Mills instantons on R4, and later generalized to more general four-dimensional backgrounds on ALE gravitational instantons. And then in this case, we have a very good understanding, detailed understanding in many ways of the moduli spaces. These are constructed as Nakajima-Quiver varieties, a finite dimensional hyperkähler quotient, combinatorily or representation theoretically attached to a quiver together with one or two dimension vectors. Then, perhaps less understood class of varieties, hopefully it's changing, is the moduli spaces of singular monopoles on R3. Okay, the kind of spaces algebraic geometrically we get are, for example, certain spaces of rational maps, in some cases between P1 to P1. So that's the second class of spaces. But my focus has always been the moduli spaces of Hitchin equation, and which is somehow the next in this natural list of moduli problems. And it somehow has perhaps the richest of the geometry, even more rich than the others. And what I will try to show you today is that in fact, just studying these moduli spaces, somehow we will already look at the other two classes as well. So somehow just the Hitchin self-duality equation also sees instantons somehow in some abstract sense, and also monopoles will show up in these studies. So it has, for the two starters, the hyperkähler metric, of course, is a family of complex structures, and we have in basically three different algebraic geometry problems whose moduli space will parameterize this underlying hyperkähler moduli space. So the first, of course, is the moduli space of Higgs bundles. We will be looking all kinds of ramifications later, so ramified Higgs bundles. There will be some corresponding moduli space of singular flat connections. These all, of course, live on a Riemann surface sigma. And finally, the representation variety of the fundamental group of the Riemann surface into groups like GL and C. So these are somehow the three reincarnations of the same space. And what's crucial is really which connects all this and somehow gives the richness to this theory, is that these three algebraically really different varieties have the same underlying differentiable manifold structure. So in particular, for us, what's important, they have the same cohomology. So you can study either of the three, and then you can conclude results, and then you can try to transfer your results to the other moduli spaces. And so basically using all these several ideas, what we managed to come up today, we still don't know what, for example, are the Poincaré polynomials of these spaces, but we have now extensive combinatorial conjectures, for example, on the Poincaré polynomial, and they use McDonald polynomials, so it's a really complex combinatorial conjectures. And so that's what we are doing. We have some arithmetic techniques, which I won't talk about today, with which we can test these conjectures on the cohomology of these varieties. And that's why I'm saying this is partly just to put it in the framework of our work, what I'm going to show you, but also is to motivate why we are looking at another somehow class of hyperkähler varieties, which of course already showed up in Philip Bolchi's talk. So this is what he calls the M-star spaces. So this really makes sense when the underlying curve Riemann surface is just S2, is CP1. And we consider then moduli spaces, these M-star spaces, which you can do both for the flat connection and the Higgs moduli space, is just you restrict the underlying vector bundle on P1 to be the trivial one. So somehow if you set up your moduli problem correctly, you look at degree 0 bundles, for example, then somehow the connections or the Higgs fields living on the trivial bundle will give you a nice open subvariety of the big moduli space. And so this was studied or is studied by Philippe for a long time, but for us it turns out that this already captures some of the non-trivial cohomological conjectures we have on all these spaces. So what we have is some conjecture which we call the purity conjecture, which says that the character variety, first of all, it has an extra filtration on its cohomology called the weight filtration coming from the Hodge structure on the cohomology, and one piece of that, the pure part, is then conjecturally should be isomorphic with the cohomology of this open variety. So somehow it says that the open enderam space captures the first layer of this extra structure we are putting on these cohomologies. So this is useful to test the conjecture because we have, as I told you, conjectures on these dimensions, for example, and then we can just count points over finite fields on this, and that's how we are testing those conjectures. So that's our motivation to look at these varieties. And then let me tell you what's the motivation from this perspective on looking at the toy models, the four-dimensional or complex two-dimensional examples, is to test the conjectures again by other means. So if you can identify the four-dimensional cases, the complex two-dimensional cases as varieties given by some equation, then you have alternative means to compute their topology, and then you can compare it to the big conjecture we have. So that was also the other reason why we have been always focusing on the surface case, because we can understand their topology independently. So let me show you then this prototype of these moduli toy models, and this is the example Nigel mentioned in his talk to start with. So it's the same moduli space of parabolic rank 2 degree 0 Higgs bundles on CP1, where we put 4 punctures on CP1 and then some full flag, or in this case just a non-trivial flag on the quasi-parabolic structure, and then some parabolic weights. Anyway, so we cook up the usual moduli space of semi-stable rank 2 degree 0 Higgs bundles on CP1. And this moduli space is identified by Boden and Yokogawa with the following construction, again explained by Nigel, is because you can explicitly construct this variety. It's somehow going to be a version of the Kummer construction. So what we do is that we take an elliptic curve times the complex line. This is an abelian group, so it has an additive inverse. We divide by that inverse. It will have 4 order 2 elements, so there will be 4 fixed points of the action, and so there will be 4 orbifold points in the quotient. We blow those up, and then we have a smooth resolution of singularities, and this space is what we call the toy model. And this turns out to be, so the elliptic curve, of course, I haven't said that, the elliptic curve is chosen to correspond to these 4 branching points. So this is a double cover over those branching points, so over CP1. So this is the Kummer construction going back to Kummer very long time ago, where he used the same construction for the case, and this is an abelian surface, and then this is the way how we constructed K3 surfaces. Then in a paper by Nigel, he looked at it more generally, where you allow this two-dimensional abelian group to be non-compact, non-projective. For example, at the end of his paper, he just mentions this example, where you take an elliptic curve times C, you can resolve it, and then he was wondering if the Hyperkähler matrix we were considering on smaller rank examples might also exist there. And then, of course, later he introduced this Higgs moduli problem, and then it turned out to be the case that in fact this construction does support a hyperkähler metric, which in fact there was a hyperkähler metric on it constructed by Bicard and Minerbe later, basically along the lines of original suggestion of Nigel. And as we saw yesterday, we don't know. We only hope that the two constructions are actually the same. In particular, that this moduli space is in fact an ALG gravitational instanton. Okay, Nigel also showed you this Hitchin map, and so you can explicitly see the map down to C, which you identify with the second component, the modulo Z2. And then you see that generically you see this elliptic curve as the fiber, but over 0 you first divide by the involution to get the CP1 with the 4 mark points. You blow those 4 points up, you see a configuration of the D4 affine linking diagram, and that's somehow the 0 fiber, and then all of the fibers are elliptic curves. And so, as I claim here, is that this metric, morally speaking, should be a asymptotically, an ALG metric. And we saw that it's non-trivial really to prove this. Okay, so then to show you the corresponding character variety, which is somehow this other algebraic variety, which has the same topology, I'll show you the corresponding character variety as well very quickly. So now this is going to be a representation of the punctured Riemann sphere at 4 punctures, and at the 4 punctures we will have monodromies, 4 2 times 2 matrices multiplying to the identity, and they should come from fixed semi-simple conjugacy classes with somehow generic in some sense. And then you look at the space of solutions up to diagonal conjugation. So that's a variety, a nice explicit affine variety, and this, if you set up correctly your problems, can be shown to be diffeomorphic with the other moduli space of Higgs bundles with this toy model. And so the nice thing about this one, and that's what I like to do, I mean, you can get equations. You can solve this invariant geometric problem, finding invariants, for example, of dissection. And here are, this is actually as a classical computation of Rick and Klein. Here are the invariants, and then what you get is an affine cubic given by a single equation in C3 of this form, some cubic equation. And so now comes the game that you can start doing. This one actually is going to be relatively easy to get a nice print, because you just choose finely the thetas. Then if you do it nicely, you will get a nice real surface now in 3 dimensions, a real slice of this character variety. So I have actually this here printed out as the file originally was courtesy of Sean Lawton. So here you can see the real points of this affine cubic, the solutions of this equation with some real coefficients, and then you can wonder about its topology. I'll show you them in a moment. Before going there, let me then show you the other one, the toy model, which is really where all this started. In fact, this was, as Nigel already mentioned, our project. We were trying to think about if we could produce something for the sculpture competition for the new institute building in Oxford. They have by now a mathematical sculpture, but at some point it was a competition. We were thinking if we could do something reflecting our mathematics, and then I was just jokingly mentioned maybe the toy model we can print or do something, but that's 4-dimensional. So I was really just joking, but I just said, what about its real points? Maybe the real points we can try to imagine as a sculpture. So, and then we were working on this. I mean, it turns out that this job is actually pretty hard. First of all, with this one, we don't have an equation. Somehow this variety doesn't embed into CP3, for example. So it's very hard to imagine how this would look like algebraically anyway in the real points. So what Nigel was showing to you was probably the best approximation you can do on presenting, in fact, the hitching vibration on this one. If you remember, he said you have the elliptic curve, the real points of this, when you choose discriminant correctly, we are going to be two circles topologically, and the two circle coming from both sides is going to degenerate into this configuration of 5 circles, D4, affine D4 configuration of 5 circles. And then he showed you this very nice picture. Especially nice was what we call the nilpotent cone, the degenerate fiber, because as in his graphics and in his video, it was very nice configuration because the circles were, for example, transversely intersecting each other as they should. But if you really want to put this thing as a sculpture, and as I did want to do it, you want to really just list the hitching fibers in a linear way, then you are forced to abandon this transversality of those circles. And so this is what I came up. So this is a topological rendition of this hitching map. So there is no algebraic geometry in here. So the idea was only to understand how the two circles become this configuration of 5 circles. So in the middle, you can see the big circle in the middle. That's somehow the remainder of the original elliptic curve modulo Z2. And then you see the 4 extra circles giving you this configuration of D4. So I actually also can show you here. So that maybe so you can see how the files are made. So once you actually produce such a file, then you have all kinds of formats. You can print them in nice forms, or you can put in slides like this. So it's very useful once you have done the job. So this was several months, by the way, even to plan it, and then it was not done by me because it's very hard to produce the file. It was done by a professional mathematician who does these printing, Olivier Labs, and so here is the result. Then the other one, which was, as I say, originally due to Sean Lawton, is much simpler because here we know the equation. So this is the character variety. And what you can then wonder is that how come that these are real slices of diffeomorphic 4-dimensional surfaces, and then that's where the fun starts. Of course, the topology of the two already is different. So this thing, the toy model Higgs moduli space does restrict to those, does retract to those 5 circles. So it has H1, 5, reflecting the 5-dimensional H2 of the original surface. But this surface, unfortunately, misses 2 of the cohomologies in H2. This H4. This, if you think about this, is just the sphere with 4 disks removed. So it has a 3-dimensional B1. So somehow, taking the real slice, we didn't do it cleverly enough. We lost some cohomology. Anyway, so then you can look at it and try to understand more and more of the topology and the geometry of these varieties. But instead of doing that, let me go on and introduce now a new, study now these spaces originally, or still studied by Philip. Even in the tame case, that was the first case we looked at, was mentioned in the introduction as a motivation in Philip's paper, where he studied the irregular versions of these. So he observes kind of a straightforward observation that the moduli space of tame connections, logarithmic connections on P1 with I don't know how many K punctures. If you write it down on a disk which contains all the punctures on a copy of the line on C, then you can write it down like this with the residue matrices at the punctures, and then to assure that there is no residue at infinity, you need to have this single equation, and then you want to fix these matrices to lie in these adjoint orbits. And that's going to be your variety. And so that's actually a pretty explicit variety. You can even forget about these connections. You just take K matrices out of some fixed semi-simple adjoint orbits, and then you look at the variety where they add to 0 and divide again by diagonal action of GLN. And then I think it was noted by Crowley-Bowie that this variety can be identified with a star-shaped quiver variety of K legs. So somehow the legs are reflecting the semi-simple orbits we put at the K punctures. And the corresponding Nakajima quiver variety, again nicely constructed as a finite dimensional hyperkähler quotient, is in fact isomorphic with this Enderam space. Okay, so for example, when the quiver is an affine Dynkin diagram, then we know that these are the examples of the Nakajima quiver varieties which give complex surfaces, and which in this case will be giving us ALE gravitational instantons. So in order to then list the examples we care about, so first of all it has to be star-shaped, and it has to be an affine simply laced Dynkin diagram, and there are 4 examples. And so these are the 4 examples. So let me show you these diagrams, because I can show you here how you can read from the diagram together with the dimension vector, which is in this case is just the primitive imaginary root for this these affine root systems. How can you read from this what is the moduli problem? So this here you see a rank 2 moduli space. Everything will be on CP1 with 4 punctures, and then this leg 2-1 tells you that you are looking at regular semi-simple punctures. At each of the puncture you have a regular semi-simple adjoint orbit to worry about. Here the E6 case you have a rank 3 problem of 3 regular semi-simple conjugacy classes or adjoint orbits, and the matrix is adding to 0 out of them and taking the quotient. So the E7 case gives you a 4-dimensional problem now with a different kind of conjugacy classy here and then here. And finally, E8 gives you a rank 6 problem, and then you can read the problem out of the Dynkin diagram. The other reason I'm showing this to you to notice symmetries of these Dynkin diagrams. Okay, of course, the largest symmetry the D4 diagram has. It has like an S4 group of automorphisms, but even the E6 has a nice S3 group of automorphisms. And what we will be later concentrating on will be automorphisms, single automorphisms. So the different ones up to conjugation will be the here a single transposition or 2 transposition or a 3 cycle or a full 4 cycle. And then here we can have a single transposition and a full 4 cycle. And here too, I mean for E7 we still have a 1 order 2 automorphism of the graph. So we will see that some of these automorphisms will be useful to understand later the irregular and star-Deram spaces. So let me then come back to this discussion. So we have now seen these 4 examples of affine Dynkin diagrams, each giving you an M-star open Deram space as an ALE space. But in fact, to each of them, so in the case of D4, had, for example, the corresponding ALE space is going to be the D4 ALE space. And again, it's very good that we have the file, the formulae I get from Sergei Cherkis, and then you can print out very nicely the D4 ALE spaces. And one issue I would like to point out, and I'll show it again in a moment, is that you can in fact read off, in the case of ALE spaces or quiver varieties, you can read off the quiver or the Dynkin diagram from the topology of the 4-dimensional surface. What you have to look at is the intersection form on H2. So if your slice is good, it captures the full H2 as H1. Then you can look at the intersection form of H1, and I mean, I don't know if you see it, you can see the 4 circles giving you the vertices of the finite D4 Dynkin diagram. So this somehow sits inside here. I mean, it's hard to imagine how, but this somehow sits inside here as an open subset, and then you somehow lose one of these circles, one of the H1s. Okay, so this is the M-star space for the toy model. Then I can also say that you can do the same story with the toy models and everything, except that I cannot print them, so I am waiting anyone who can tell me how these looks like in the real, the E6, E7 and E8 teaching fibrations, and then you have the same story for them. You can construct them with the elliptic curve modulo not as Z2 symmetry, but the Z3, Z4 and Z6 symmetry, so those are more special symmetric elliptic curves. Okay, so that is about this tame story. Let me also, just for the sake of to be in the picture, we have heard this already, of course, is that all ALE gravitation instantons are in fact shown to be isomorphic as varieties, as quiver varieties of affine Dynkin diagrams. And or actually they are isomorphic as Hyperkähler moduli spaces if you put on the Hyperkähler metric. And so for this you have to recall that you have this AD classification, and so to each of these affine simply laced Dynkin diagram you can attach a complex algebraic variety, this ALE space, which comes with a family of natural Hyperkähler metrics on them. So I again can show you two more examples just because I have printed them. Again, the technique is that you have to find an equation, an equation which describes in three variable equation in C3, and then if you have to find a good real slice to capture the topology, and these two examples, the A4 and perhaps the most complex is the D5, show you again this principle that if you have a good slice, then H1 is going to be with the Z2 coefficients will be isomorphic with H2 of the original surface, and then you do see the intersection form over Z2, in fact, because in fact these circles have zero self-intersection here, but they do nicely intersect each other. So you do see 1, 2, 3, 4 circles lined up like in the A4 finite Dynkin diagram, and here it is the most interesting one because it's not really symmetric, is you can see the D5 finite Dynkin diagram as the intersection form. So these bottom two circles are these two circles intersecting with this central one, and then you have two more in this leg. So here it is. You can nicely print them out, and you can wonder how the topology looks like. You can really touch those nodes of the Dynkin diagram. Okay, so this is basically was the fun part of the talk, and let me now report on some observations we made which came out of our studies of the arithmetic of irregular M-star de Rham spaces. So again, this we will follow mostly Philip Wolch and Bremer and Sage work in the twisted case. For simplicity, I will consider only the order 2 cases. So an order 2 irregular connection will have a formal type around one of its singular points. There is some formal gauge transformation you can make to bring it to this form, where this form is going to be fixed. So you are fixing this formal type, a matrix A1 and another matrix lambda. In this first case, which we call untwisted case, this is the case which is studied mostly by Philip, is the case when A1 and lambda are supposed to be both diagonal, and in this case we assume they are both regular semi-simple fixed matrices, and we will fix, when we look at the moduli space, the formal type of the irregular connection around its singular point, one of the singular points like that. Then there is another class which we have more recently looked at, because the description of the moduli space is more recent, is what we call the fully twisted case, when A1, the leading term, is no longer semi-simple. In fact, this one now we will have to pick as a nilpotent this elementary matrix, only one on the top right corner and zero everywhere else. So it's a nilpotent matrix, and then we have to have a very specific form for the residue matrix. We have n minus, which is the full nilpotent block, but lower triangular, so it lives below the main diagonal of the ones, and then you have a scalar matrix on the main diagonal. So anyway, so this is some technical reasons we pick these examples. And then now I'm going to describe to you, as the result of Philippe and Bremer and Sage, what's the description of the moduli space, of the M star, the RAM moduli space in this case. So the construction goes by abbreviating things. So we will abbreviate GLN to be G. We will have T flat to denote the center of GLN, the diagonal matrices. We take the maximal torus, and then U is going to denote the maximal unipotent subgroup, which is the unipotent radical of the Borel. You can think of this as upper triangular matrices with one on the main diagonal. Okay, and then what's important for us in the construction is that T star G first as a complex symplectic manifold has a Hamiltonian action by G times G. G, the first G acting from the left on G and the induced action on the cotangent bundle, the second from the right. And so using this action, you can, as a complex algebraic variety, you can describe the M star Deram space as follows. So the setup is the following. So you have P1. P1, we will have KU untwisted punctures where we fix some generic lambda of this type, some formal type like this. These are the untwisted punctures. Then you have the twisted punctures where we fix some data like this at KT points, and then the remaining KR points we will fix some usual logarithmic data that is fixing the adjoint orbits at those other punctures. So with this data, things are chosen generically to get a smooth moduli space. You can describe your moduli space as a GIT quotient or an actual complex symplectic quotient like this. So you take here first, you take T star G, you act with the maximal torus from the left. You take a symplectic quotient at the level dictated by this lambda. Then you take T star G at the twisted functors and divide by the unipotent matrix. So this is now a non-reductive group. So algebraic geometrically you have to be careful, but complex analytically things are fine. Times the center, and then you can divide. Again, now you have to take a particular, so the center here will be given by this lambda 0, and then in U, the Lie algebra of U, we have some very nice element, which is the center, in fact, of the Lie algebra of U, where we take the quotient. So then you take this quotient, and this is basically the same quotient construction as we had seen in the Tame case. So we just take the adjoint orbit, one for each, and then you multiply all this data together and divide by the symplectic quotient by G. So this is the moduli space. Okay, great. So then you can start to study this. So Philippe has been doing this for a long time, and he basically finds that in case you only, when you have so Philippe, as I say, until recently concentrated on the case when KT is 0, there are no twisted punctures. So there are no twisted punctures, and you have only one irregular singularity. In that case, Philippe basically can prove that what you get, the variety as a complex algebraic variety, is a Cuvier variety of Nakajima. So in particular, in these cases, you get for free some Hyperkähler metrics on these varieties, even though it's unclear what the moduli space meaning of this metric is. But somehow this misses the case when you have more than one untwisted punctures. To deal with the case of more than one untwisted punctures, there are other works, but there is this work which is basically was done by Yamakawa, who looked at Cuvier varieties, what he called with multiplicities. So his work works very nicely for the rank 2 case, but for higher rank it has to be modified a little bit, and fortunately we have a recent work by Geis, Leclerc, Schröer, who attaches a preprojective algebra, generalized preprojective algebra, to a non-simply laced Cuvier, to a non-symmetrizable Cartan matrix. And so if you look at the preprojective algebra from here, which is a slight modification of the work of Yamakawa, and then you follow what Yamakawa did. You can also construct a variety, which we can call a non-simply laced quiver variety, for example, attached to a non-simply laced quiver and the dimension vector. Well, what's the key, what's the difficulty in this story? It's a bit like this here, is that in the quotient construction, you have to divide by a non-reductive symplectic group. So you do this formally or analytically. When you do it algebraically, you have to be careful. Okay. And so what was very nice in the work of Yamakawa, that in the n is 2 case, when the rank of the bundle is 2, he had this observation, which then, if you modify his varieties with the new preprojective algebra of Gauss, Leclerc, Schröer, you can actually easily extend Yamakawa's result that the M star de Rham space in these cases, but I think we can prove it for any case considered by Phillips, so all the case when everything is semi-simple or diagonal. You can always show that all of them are very naturally can be read off. They are non-simply laced quiver varieties. And so, okay, we are interested in the toy model, so we are interested in the cases when they are surfaces, and they are going to be surfaces, for example, when they are attached to now non-simply laced affine quivers. So it has to be star-shaped in an analog sense as before, but they have to be star-shaped non-simply laced affine quivers. In this case, the corresponding variety here, which then is the same as the M star de Rham space, is going to be a surface. Okay, so let me show you this list of the more cases of affine star-shaped Dynkin diagrams, which are in this case non-simply laced. So there are 7 of them. So I have here in the notation what I have added with blue. I added, of course, the dimension vector of the primitive imaginary root, which will be the dimension vector. And then I have the classical notation with the non-simply laced edges, which somehow shows how the Cartan matrix is not symmetry. But there is an equivalent notation. Basically, I think this is already in Yamakawa's work, where sorry, this is a double notation. You can forget about these modification on the edges and just concentrate on what we call the multiplicities. So this multiplicities gives you the diagonal matrix which symmetrizes your Cartan matrix. But okay, and then here you see the examples, and what's also very nice of these examples, that they in fact all come from folding the simply laced affine Dynkin diagram. So folding, as I mentioned, the folding is an automorphism of the affine star-shaped Dynkin diagram. So here, for example, you can see the folding of D4 with a single transposition. So 2 of those things, you would make this automorphism of D4, and then here you see the corresponding non-simply laced Dynkin diagram, and in fact the 2 will turn out to be precisely the number of elements, order of the folding. So here you see an order 3 folding of the D4. In fact, this is aptly called D4-3 because it comes from D4 with the 3 cycle of the folding. This one, C21 again, comes from D4, but now the product of 2 transpositions, disjoint transpositions. And it turns out to be the same as the C2 affine Dynkin diagram. And then you see what is called again A22. I'm using here Katsi's notation, so this is different slightly than what we had before. And this one comes from again D4, but with the 4 false circles. So these 4 examples were relevant for, or were already in the paper of Yamakawa. These are all correspond to rank 2 M star de Rham spaces. So I can read off from all these spaces the moduli problem. So these are all star-shaped. You have a central vertex with a 2 on it because it's rank 2. And then you have smaller numbers on the legs. And then when it's this is going to be a tame leg, so it's like just before. This is a 2 ordinary tame singularity, but one singularity will be of order 2. here again, one singularity of order 3 and one tame singularity, two singularities of this setup. Here you have two untwisted singularities on P1, and here you have an order 4, which I haven't described, but you can describe the order 4 singularity as well on P1, a single order 4 singularity. So these were all considered by Yamakawa, and he proved that the corresponding non-simply laced Kuiper varieties are isomorphic with the M*-Deram spaces. And here are the three higher rank examples. So for G2, affine G2 linking diagram, you see this is a star-shaped Kuiper with 3 being the rank of the vector bundle. On P1, you see an order 3 twisted. Okay, again, this one I didn't describe for you because it's order 3, but there is anyway an M*-Deram space whose moduli, which is isomorphic with the non-simply laced Kuiper variety you attach to this Kuiper. Then you have E62. This in fact comes from the E6 linking diagram with this take quotienting by the involution of the transposition of 2 of the legs. So here you see this double leg, and this corresponds to, on P1, rank 3, 2 punctures, 1 tame puncture with regular semisimple conjugacy class. I read this off from the 3 to 1, and then I have Phillips order 2 regular semisimple leading term M*-Deram space. And finally, we have F41, which comes from E7. So this comes from the E7 linking diagram. Here you see the 2 long legs of the E7 linking diagram coalesced into an order 2 or a multiplicity 2 leg. You see regular semisimple leading terms. It's an order 2 singularity on untwisted singularity on CP1 with a regular semisimple leading term. And here you can read that the other one is a logarithmic, a usual tame singularity with this kind of semisimple adjoint orbit, 2 eigenvalues, and they both with multiplicity 2. Anyway, so this is a very nice way to read off the moduli problem from a star-shaped, non-simply laced linking diagram. Okay, so this was just a mild observation. Basically, it's due to Yamakawa, except that he had a slightly simplified variety which differs from the Gauss-Leclerc Schröer equations from in the case when there is an edge with the 2 vertices being the 2 multiplicities being non-coprime, and in each of these cases you have this edge where his definition differs from Gauss, Leclerc, and Schröer. Okay, so then finally, because this has metrics on Hyperkähler moduli spaces in the title, this conference, so what we then managed to also find is a simple observation, but then it's really fun because then you can combine this observation with arithmetic studies, and then we will be doing some exotic things at the end. So, but first, let me note that this construction of Philippe Bolch and Bremer and Sage for the M*-Deram space using T star G and quotients from the left and right can in fact put on a natural Hyperkähler metric. And the reason we started to look at these Hyperkähler metrics was in fact to me a mysterious quote in the paper, or several papers in fact, of Phillips. He says that basically he was arguing that in not all cases his Kuiper variety constructions will work, because in particular in the case when you have CP1 with 2 order 2 untwisted irregular poles is not a Kuiper variety, because it's what he said was the D2 ALF space. And so I was really confused. I didn't know, I think, that much about the D2 ALF space, and but now I learned this, so I can tell you that this is part of the classification scheme. In fact, we heard about this already, of course, many times in this conference, of ALF gravitational instantons. So I'm just recalling for you something we have seen. This goes back, I think, to the work of Cherkis-Kapustin, and there are now many nice results which prove parts of this conjecture. So the conjecture is that we have 2 infinite families of ALF metrics. One is labeled by the AN Dynkin diagrams, the others by the A, D, and Dynkin diagrams. Basically, when n is greater or equal to 4, when n is 3, D3 is thought to be A3. And then we have this 3, in fact 4, because A02 is somehow an exceptional case. So in the case when D2 is corresponds to this case, and this turns out to be precisely the paper I already mentioned, where this Kummer construction was discussed by Nigel. He constructed a hyperkähler metric on the deformation of the Kummer construction, but now for C times C star, not Z2. Then D1, okay, this is all weird because I don't see a D1 Dynkin diagram, but this is somehow notation. I think along the line of the ALG idea is that we have the D1 parameter deformation of the Atiyah-Hitchin manifold. In fact, there is no, it's not the Atiyah-Hitchin, it's the universal cover of the Atiyah-Hitchin, which is a Z2 fundamental groups. It's the universal cover. And then you have a one parameter deformation found by Denser. And finally, D0 is supposed to be the Atiyah-Hitchin manifold, which is somehow rigid manifold, hyperkähler manifold, really famous. And I also spent a lot of time, of course, in terms of the sense conjecture about the L2 cohomology. Okay, so now let me show you that we can in fact recover some of these, and I think hopefully all of them, by this construction on natural hyperkähler metric on irregular M star de Rham spaces. So the construction is really just looking at the complex algebraic quotient and making it hyperkähler quotient. It's not entirely straightforward because not all the quotients were by reductive group. When it's a reductive group, then it's straightforward. So we take, first of all, what's important is that the total space, in fact, has a natural hyperkähler metric because the cotangent bundle of the group G has a natural hyperkähler metric constructed by Kronheimer. And we have the maximal compact subgroup. To do hyperkähler quotients, we take a maximal compact subgroup, which acts by hyperkähler isometries. And then another input which is needed to understand these non-reductive quotients. So Roger Bielawski has a very nice construction using these Lodovi slices, which gives a natural, complete, I think, hyperkähler metric on precisely these complex symplectic quotients which we need. And so now combining these, this really is just a simple observation, is that now somehow with these works we can put some sort of, I think, complete hyperkähler metric on all these M star de Rham spaces, because we just take Kronheimer's metric on the T star G's. Kronheimer also constructed hyperkähler metrics on these adjoint orbits. So you put that there, then you have to divide here by T, which is a reductive group, so you have the compact, maximal compact subgroup, so you can do hyperkähler quotient here. And the only tricky thing is the unipotent group, but then you use Bielawski's work. And then eventually, again, you divide by a reductive group, so again, you can make it hyperkähler. So it's a really simple observation, putting things together from the literature, but that says that somehow these irregular M star spaces of the type we are considering will carry a natural, I think, complete hyperkähler metric, which is going to be different from the Nakajima, the ALE metrics. Is it? I haven't done it yet, but they are not unrelated, right? The Bow variety also uses the same spaces, but so far I haven't managed to. I mean, I am looking at Bow varieties and trying to find the corresponding ones. I think maybe that's the difference when you have a loop, then, but I haven't managed to do it yet. Okay, and then let me then now give you some lists. So then it was great. So then in some cases, now we can construct complete hyperkähler metrics, and then you wonder what is their asymptotics. I actually expect, because it comes from some NUM data, that in the case when they are surfaces, maybe they will always be ALF. But then originally these two cases were, these three cases were missing, the D2, D1, and D0. Somehow they were not, didn't show, the D2 showed up, right? The D2 showed up on our list of affine non-simplicial Dynkin diagrams, but where was the D1 and D2, D0? And then it turns out that you have to twist the singularity, and in fact it turns out that Philip already knew about these constructions. As we could see in his talk, he did call these things D1 and D0, so it's in fact not new, but we also observed, so first of all we observed that if you take this, pivotal figure where Philip noted this, that it has to be the D2 ALF space, the metric you get on the nose is somehow, basically you can identify it with some monopole moduli space, and it turns out that, or conjecturally, at least for me it's conjecture because I don't really understand these constructions, this should be the D2 ALF gravitational instanton with its Hyperkähler metric, which was constructed by Nigel. Then you have the case when you, the same story, so you have two punctures on P1, but now one is twisted and the other one is untwisted. And again, you have, this is the quotient construction you have to make. And then now, again, you can see that this is some kind of monopole moduli space. And I think Sergei in this case assures me that this indeed is going to be the D1 ALE space, ALF space of dancers. What we did do, because we are more algebraic, we could of course compute the underlying complex algebraic variety, and we did see that they are really the same, and I think that's what Philip did too. And finally, most excitingly, the Atiyah-Hitchin space also shows up as an M-star Derham space in the case when n is 2, and you have two twisted irregular singularities, then you just see this quotient construction, one of the central torus you can forget about. And then you really first divide by the central torus to get T star PGL2, and then you really see the Roger Bielewski's and non-data construction of the Atiyah-Hitchin manifold. So this was really great. So finally, Atiyah-Hitchin manifold can be put on as a moduli space of objects on a Riemann surface, together with the natural Hyperkähler metric. And then, for me, even more excitingly, this construction extends for higher n. So for any n, I take an irregular connection on a trivial vector bundle, two twisted irregular singularities of the type I showed you. And then, again, the moduli space, just because of the theorem of Bremer and Sage, is going to be this. So on the nose of this is nothing but the moduli space of based SU2 magnetic monopoles on R3 of charge n, and this is basically the space where all the sense conjecture and all these problems live. So it's fantastic that somehow this space now shows up as an object on a Riemann surface as well. And for us, let me just give you all this result, which really comes from our arithmetic technique. So we do count points over finite fields on this. And we have this very nice result, simplifies enormously. The number of points on this variety over a finite field will just be a q power to the dimension of the variety. And then we can in fact show more that the computation is motivic. We can show that the motive of the variety in the Grothendieck-Ring of varieties over the complex numbers is actually the motive of the affine space. Okay, so why it's nice to me is that because this really is you can deduce the same thing from Siegel and Selby's work, which really was the first non-trivial contribution towards proving the sense conjecture. They proved that this based moduli space, which is non-simply connected, the real conjecture was of course on the universal cover, this one is going to have a trivial cohomology, and therefore the count must be a q power. In fact, I think as we speak, my collaborators are also working out the case when you replace GLN by SLN, and in that case, I think we are going to see precisely the Siegel-Selby result on the universal cover of this magnetic monopole moduli space, and then we will be exactly the place where the sense conjecture is. Okay, just to finish, let me give you some problems, because we were asked to give some problems. So the last slide contains 3 problems, and I go through very quickly through them. So we have the first question now is that maybe so there will be more examples of these M-star Derham spaces, open Derham spaces, which will be isomorphic to moduli spaces of certain maybe singular magnetic monopoles. So that's my question, which one of them, or how can you identify them with magnetic monopole moduli spaces? And then in particular, maybe some or maybe all, or which ones, which non-simply laced Cuvier surfaces, that is ones which corresponds to non-simply laced affine linking diagrams, support natural ALF metrics. And here I don't just mean the star-shaped ones, the 7 examples I showed, but there is a very long list, I mean several infinite lists of affine non-simply laced linking diagrams, and they all give by the GLSY construction, they give you a non-simply laced quiver variety. They are all surfaces, and maybe we can construct hyperkähler, natural complete hyperkähler metrics from them, and asking which ones might be ALF. So of course I showed you the first question is that in this particular case the magnetic monopole moduli space has a description like M star theorem. Then I showed you that we have a hyperkähler metric in the case when it's in star shade. Because I use the T star G, potentially I will get ALF metrics. I expect to see ALF metrics. And so in one more infinite class, we can construct hyperkähler metrics on these non-simply laced affine quivers. And these should be the Dn ones, the Dn ALF spaces, but again, I cannot prove it. Then the second question is we can describe the elliptic Hitchin fibrations, the actual fibrations with all the singular fibers for star-shaped non-simply laced affine quivers. So this describes the potential cases when you have a surface. And here, of course, we will expect ALG metric. Okay, we know how the fibration looks like for D4, E6, E7, E8. In the rank 2 cases, we have a conjectured description in Tom Sutherland's thesis coming from work from physicists of Gayoto, Moore-Naitsky. And according to Philip, in fact, the rank 2 cases are exhaustive. So probably we now have at least conjectural description of all these elliptic fibrations, which can arise as Hitchin systems. But it would be nice to really prove them and understand them. And especially because then we might be able to print them. And for the printing, I have a mathematical problem. So you take a gravitational instanton, and which ones I can arrange so that the real slice catches all the topology, in the sense that H2 of the gravitational instantons with coefficients from Z2 is actually isomorphic with the cohomology of H1 of the real slice. So here I have the examples. I showed you this one captures H1, H2, but this one doesn't. So I don't know how to modify the Frick-Klein surface to see all the 5-dimensional middle cohomology. Maybe it's impossible, I don't know. But all the other ones, I also have the Eguchi-Hanson, the real points of the Eguchi-Hanson. Of course, it has a 1-dimensional H2, so you can see this here. I can see through that. And you have D5, D4, so all the others are correct. And the nice thing is that if you give me more examples, then we can continue producing these. And then there are shops now on the internet where you can actually shop for these gravitational instantons. And you can get these ones. Okay, thank you very much.
So your two examples right at the beginning, you had a real slice of the character variety, was that right?
Yes.
I mean, in a way, there's no reason to suppose that should have the same topology as the real slice, because, I mean, the real slice in the Higgs bundle complex structure should be holomorphic. If it comes from a real structure on the curve, it should be holomorphic in the character variety complex structure. So this torus with 4 points missing, which is the imaginative model, it should be some holomorphic curve in this affine cubic. So I mean, your question about capturing topology is, of course, independent of that, but I don't think there's any contradiction in saying that the real slice...
No. I didn't indicate the contradiction. I would like to see myself a model of the Frick-Klein surface where I can see the 5-dimensional H1. It probably is not possible because you play with this and I only see 3 of the circles, and maybe there is some deep reason why we cannot see that. But there is no contradiction indeed. You don't expect the two, there is no map between them, so that's, yes.
Although, if it does come from, which I guess it does, from the, if you put your 4 points on the 2-sphere on an equator, then I guess the involution, the real structure, probably is inducing the one that we were discussing. then you ought to be able to calculate that fixed point in the character variety by using the Hyperkähler coordinates. I mean, if you just changing
Right, that's a good idea.
generators.
That's a good idea. Very good. Because it's also analogous to how we were thinking about this, right? So here we also wanted the 4 punctures to be real, and yeah. Yeah, but then if someone has to do an intelligent computation with the Frick-Line equation, and I haven't been able to do it yet.
You constructed Hyperkähler matrix on this spaces with irregular singularities
Yes.
on a finite dimensional Hyperkähler explosion.
Yes.
The other one, there is a Hyperkähler metric which comes from considering them as moduli spaces of connections. So you seem to assume it's the same metric?
No. One is complete, the other one isn't, right? Because the other one, the first one, the natural one, comes in. You need some other stuff to it there, and then it will be complete. So this is very similar to what Philip was doing, but for Philip, he would put an ALE metric on them, on some of them, and that was the same question. I mean, he asks it everyone, the experts. I don't know where he is. But yeah, that what's the connection between the two metrics? Can you perhaps interpolate from the ALE or now the ALF metric to the ALG metric? But I don't know any answer.
Yeah, thinking about our conversation yesterday about the Moore Takakawa paper, they want to associate two surfaces with various numbers of punctures of Hyperkähler, or at least holomorphic symplectic space, with an action of several copies of G and a symmetric group. So the case of 2 punctures is just T star G. Is there any way, if you chose your parameters suitably in that construction, you could get the one of the 3 punctures that they're looking for, or don't you get a big enough group action on your space?
So I'm not sure if... So you want the 3 punctures and...
Yeah, so they want a space with an action of an action.
That's what we see, right? I can show you.
3 copies of G and the symmetric group on the 3 letters of them.
So what we could put 3 punctures, and then you can have something like this kind of Slodový slice business of Roger Bielewski, or you can take this one. You can probably modify it to some other parabolic subgroups, but I don't know if you what exactly is your freedom. This is very new, so this is very recent. I just learned about that paper yesterday from you, so I hope there will be connections there. Yeah.
So for the second problem on your last transparency, can't you just take the lax pair for the panel of A equation and compute directly what the elliptic curves are?
Yes, I am sure you can. Please do. So, yeah, this is a great possibility. But so Tom Sutherland gives me the list. And what I use the list for, by the way, is that I then can compute the cohomology. In that case, the perverse cohomology of the irregular, the Hitchin system. And then I look at my conjectures, which are some giant combinatorics, and then I extract from those cases, and I beautifully get exactly the ones which I can match with the precise description of the Hitchin system. So then I have a theorem on those cases about the perverse Hodge polynomial of the Hitchin system. Yeah.
If there are no other questions.